Okay, my mic is on, push the down button, and the clock is ticking at the start. So I'm a sculptor, a mathematician, and my passion is to sort of combine those ideas, and to take this sort of love of geometry and mathematics and art and convey it to people. And what I'm going to show you here is a talk on what I call Geometry Ascending a Staircase. This is the name of a sculpture which you're looking at. This is at Duke University. I installed this last October. And I want to take you through the process of what I go through when I sort of think of a sculpture and work on it for about a year. So what you're seeing here, first of all, is a plan of the building, a 3D model that I made based on drawings I got from the site. I was commissioned to create this sculpture there, and I looked at the atrium that this is in. It's 75 feet tall. I planned these 4 different orbs that go there. There's an evolution. The one that you see on the top left is actually the lowest one in the atrium. Then as you go up, they're 4 feet, 5 feet, 6 feet, and 7 feet in diameter. And the design changes slightly as you go from one to the next. Here you can see they're each made out of a flat piece. So the one on the left is the first sculpture, the second one is the second sculpture. There's a fold in the middle that grows, there's a slight change, and there's a big difference in scale as they go from a 4-foot orb up to a 7-foot orb. I took my designs and sent them out to a laser cutter that can cut out the metal. This is 6061 T6 aluminum. It's a structural aluminum with holes in the right places and brackets I made so that it can bolt together. And I put together this prototype in my studio in Stony Brook. And that's a smaller one. For this larger one, I just had a sculpture party. So I just called up a bunch of friends and said, faculty and friends, come on over to my house and we're going to test build this sculpture. And what you can see here is the 7-foot one, halfway height. And then having done that, for the actual construction, I designed a sculpture barn raising, where we just put up announcements on campus, come to the sculpture barn raising. And the parts I had powder coated in 4 colors. They go from red to 2 shades of orange to yellow for the highest one. And people came here, and I would walk around between 4 tables and give people instructions on what to make, how to build it. It's a rather intricate set of rules as how these parts go together. But the way this comes from the mathematics that each sculpture is made of 60 planes, and the pieces are identical in each sculpture. So there's 60 parts here that go around, and they have to fit each other precisely. So it's not something you can just sort of doodle a shape and expect it to exactly fit. You have to calculate very precisely. To have these planes all working together, they define planes in space, and wherever 2 planes meet, there's a line, and that line will be the intersection of the pieces. So I'm working with a kind of a canvas, which is a set of planes symmetrically arranged in space. And I design how the parts go, and then I can sort of use the mathematics to work out the lengths and the angles. But I only have to get from one spot to another spot to make these meet. In between, I can take a short path or a long path, or I can make it curvy or pointy. So that's where the artistic side comes in, and I can design these pieces as I like to make a sculpture that's visually engaging. So here, for the barn raising, what you're seeing is building first a kind of an equator, and then adding parts that make a hemisphere, and then we'll turn it over and add another part. But the fun thing is that the whole community comes together and builds it. In fact, it creates a community. From now on, anyone who ever goes back in that building who built it will point up to this sculpture and say, I helped make that thing. We're hanging it there for, presumably 100 years or longer, and they'll feel like they were part of making that happen. So to back up the sort of the theory of what I'm doing, I think of this as kind of the mathematical analog to a ballet or an opera or a theater performance, where these people are in some sense the audience. That they're learning about math, that I've sort of imposed this construction on the conductor and having them do this. But as they do it, they have to participate in the math to do it, to appreciate the math, to appreciate the beauty of it. So these events are these events where they're receiving kind of a math, but in this informal way, that I can stop and I can explain things when they ask a question. I can point out the symmetry. I say, the 5-fold axis, the 3-fold axis. Can you find the 2-fold axis? We can relate that to an icosahedron or a dodecahedron. Has the same underlying symmetry relationships. So I can get people to think more abstractly about not just the surface, but as mathematicians do, to look for the patterns that are underlying the surface that repeat in all sorts of other structures. You can imagine there's all kinds of engineering aspects as well, making these things strong enough, calculating the weights and the tensile strength of the material so that it's not going to fall apart. You can't hang this thing up. So it's a balance of art and mathematics and engineering all together in one big event. And if you want to learn more, you can go to my website, georgehart.com. less more pictures and a video of being installed. I think I did that in 5 minutes.